down from the board as far as steps. Just remember, this is recorded, so it might be easier to just kind of follow along, watch, and then you can go back, look at the recording as I'm going through the different problems. As I've already sent out what the answer, you already have the answer key as far as just what the solution is. We're going to go through the process on each problem for getting that solution. And these will be common ones that we'll see on the final. Right? First one I have there is a piecewise graph. Okay? And on a piecewise function, 2 pieces, 3 pieces. A lot of times we'll see 3 pieces more than 2. It doesn't matter how many pieces that there are. When we're looking at a piecewise function and creating the graph, what we want to do is the first piece. When I'm done with that, I do the second piece. When I'm done with that, I do the third, so on and so forth, however many pieces we've got. Okay? So it's best to realize what it is we're graphing. Right? Is it one of our library functions? Is it a line, a horizontal line? And at the top here, this x plus 3, well, that's just a line with a slope of 1. So we have a linear function. Typically, when we have a linear function, the easiest way to graph it is by getting 2 points. Okay? So I'm going to find 2 points on this y equals x plus 3. And I can use any 2 points that I want, but the 2 values I'm going to use for x here are going to be the bounding points. It said that x is between -7 and 2. Okay? And so I'm going to use that left point of -7, left x value of -7, right x value of 2. And so if I put -7 in, I'll get -4, -7 plus 3. 2 plus 3 is 5. Right, so -7, 4 is going to be about right here. And as far as up on the board, I'm just going to kind of estimate it. On your paper there, definitely much clearer. On a test, you're given a nice grid, things like that. It would be a solid dot because I do have the equal to, and it's going to go to 2, 5. So that'd be about right here, and I'm going to have an open circle. Open circle because they don't have the equal to. I finished the first part. Now I'm going to the second one, that f of x equals -4. Well, f of x equals -4 should be a horizontal line at -4. But it only has one x value, just at 2. So it's just the point 2, -4. Estimated about where I said that was 2 before, so I'm going to estimate that at 2, 4 again. Paper test, paper that you have in front of you, you've got a nice grid on there. You can keep things nice and neat. And then my last part, -x plus 4, that's another linear function. So I want 2 points. And this time I'm just told x is greater than 2. Right? So I'm not given like the first part where it was bounded between 2 values. So I'm going to start at 2, since it says greater than 2. If I put 2 in, -2 plus 4 is 2. So that's going to give me the point, let's see, 2, 2, so about right here. And it would be an open circle, because again, I don't have the equal to. And then it just says x greater than 2. So this part's going to go to infinity. In other words, I'm just going to have a line drawn with an arrow, but I need to know what the direction the line is going to be in. So I need another x value. I would just use 3. Anything greater than 2 will work. I'm just going to pick 3. So -3 plus 4 is 1. Set a point about right here. And just continue that down and get an arrow on the end of that. That would be my piecewise graph, all 3 parts. When you're graphing a piecewise function, one thing that you can check on is the fact that they can't overlap anywhere. Okay, so if you have your graphs overlapping, in other words, wouldn't pass the vertical line test, something's wrong. That's what's going to tell me that when I see these points lined up, only one of them could be closed. Now, it's possible that none of them would be closed, but definitely only one can, because if more than one was, wouldn't pass the vertical line test. All right, problem 2. We're asked to do transformations on the library function y equals square root x. Now the transformations, we don't really care what the original library function is we're starting with. We need to remember that if it shifts up or down, that would be added or subtracted on the outside. Shifts left and right, that would be on the inside. Some things like that. Now, typically when we see this question come up, we're given a specific order to do the transformations in. So I've got to make sure I do it in that order. So the first thing it's telling me is that it shifted down 6. So to move it down 6, that would be minus 6 on the outside. That has now moved the graph down 6. The second thing it has told me, reflect about the x-axis. So if I'm going to reflect about the x-axis, that would flip the graph upside down. That is when we have a negative coefficient. So that would be negative, and it's of the whole thing. The reason it's of the entire thing is because that 6 was already there. Okay? The function was root x minus 6. I'm reflecting the entire function. So it's going to be a negative in front of all of it. So once again, I'm going in order of what I was asked. I was asked to shift it down first. Now the reflection. There's nothing wrong with this right here, but typically I would go ahead and distribute that negative. So we'd have negative x plus 6. And then the last part says shifted left 7 units. So y equals negative square root, left would be the inside. So it's going to be x plus 7 on the inside. And then we still have that plus 6 on the outside. So we want to make sure when we're asked to do or work with our transformations on a particular function, we go in the order that we were asked to do. If you go in a different order, it messes up the signs on the final answer a lot of times. So make sure we go in order, step by step. Okay? In a grading process, for example, let's say you said, hey, plus 6 here. All right. Well, then you would end up with a minus 6 here. You can get partial credit. So you would have lost a point for that plus 6, but you still applied the negative correctly. You still applied the 7 correctly in there. So it's good to show each of your steps as you're going through instead of just writing one final answer in case you made a careless error or something somewhere in between there. Okay. Third one. Just write my function down here. We're asked to use the difference quotient. Now, the difference quotient is one of those things that you don't have to memorize. If you're asked to do it, it will be presented as such. Hey, go find this. Okay. Same as it was on an earlier exam. So f of x plus h means x plus h is being substituted in for x. So that would be x plus h squared plus 6 times x plus h plus 9. So I've substituted x plus h in for each x minus the entire f of x, which would be x squared plus 6x plus 9. Notice I've got parentheses around that because I'm subtracting the entire function. That means I'm going to have to distribute that negative. And then the easy part, just over h. Now, before you go any further, double check when you're working a problem like this out, this part's correct. Because the rest of the way is just the tedious work of multiplying things out, combining like terms, In other words, old stuff you've done many times, and yes, we make careless errors and things, but we want to make sure that this part's right. So this first part, f of x plus h, I have substituted an x plus h in for each x. Got my square in there of 6 times, minus my entire function, that f of x, and then all over h. Now let's get this multiplied out. X plus h squared. That is x squared plus 2xh plus h squared. Distribute the 6 plus 6x plus 6h and plus 9. Distribute my negative. Minus x squared minus 6x minus 9 all over h. Now, typically on the multiplication, things like that, I usually see the mistake happen right here. Now, I usually remember distributing the 6 or distributing the negative. It's this 2xh. Just a little reminder here. If you have x plus h squared, x plus h squared would be the same thing as doing x plus h times x plus h. So there's my x squared, xh, xh, h squared. So there's where we're getting that 2xh in there. Sometimes we're pretty good at just going right through and going, all right, this is this. Other times we're not, and we just need to go out to the side and kind of write it out to make sure we're getting that going. Oh, let's see, x squares cancel. 6x's cancel. 9's cancel. And let's see, that leaves me 2xh plus h squared plus 6h all over h. One checkpoint right here is all of these that were from the original f of x should cancel with some earlier term. Should cancel with some earlier term. Now, when I see that h there on the bottom, I look at the numerator. And wait, there's an h in each term of the numerator. So I can take an h out of each term. In other words, I can divide this h into each one. So my final answer would be 2x plus h plus 6. And that would be the final answer I have, or should have anyway, on the key that was sent out. 2x plus h plus 6. It doesn't matter the order of the terms. Typically, they'll end up in that order just because of the multiplication and simplifying. That was the order they were in. Fourth one. Even, odd, or neither. And I have 3 different ones here just so we can kind of get an example of each. Even, odd, or neither. Back from one of the earlier lessons, that first unit. Typically, this becomes one of those that students forget. All right. Since it was earlier on, and it's not very straightforward what you're supposed to do. I mean, this one's earlier on, but it's pretty straightforward what you're supposed to do. Hey, I've got to get f of x plus h, subtract f of x. It's kind of telling me what to do, even if I don't remember it so well. This one was asking, are the functions even, odd, or neither, but not giving me any direction in the problem as far as how to figure that out. So, figuring that out. we always found f of negative x. When I'm asked to figure out if a function, the algebraic function, again, without looking at the graph, if it's even, odd, or neither, I'm going to find f of negative x and see what I come up with. So f of negative x, negative 3 times negative x to the fourth minus negative x squared. Let's see, a fourth power on a negative x is positive, so that's going to be just negative 3 times x to the fourth. And then that will stay minus x squared, because negative x squared is x squared. Then I examine what I came up with. If I come up with the original function I started with, it is even. If I come up with the negative of the original function, it's odd. If I don't come up with either one of those, then it's going to be neither. So I look at my function that I'm presented with there, or what I found. I got negative 3x to the fourth minus x squared. And then I look back at my original one, and I'm like, oh, wait a minute. Those two are the same. That means that this function is even. Those two are exactly the same. Even graphically meant that it had y-axis symmetry. Symmetry over the y-axis. We're not going to see a graph, we're going to see a function notation. And decide, getting that f of negative x tells me if it was reflected over that y-axis or not. Second one, f of negative x. 9 times negative x cubed plus 3. So if I cube a negative, I get a negative. So that would give me then negative 9x cubed. I have negative x cubed, so negative 9x cubed. And then I still have the plus 3. All right, so there's what I end up with. I'm just gonna, so examine what we ended up with there. I'm just rewriting that third one up here a little higher. We got the same as the original, even. Well, that's not the same. It's close, but it's not exactly the same. So it's not even. Odd, the negative of the original. Okay. This is not going to be the negative of the original because the sign on the 3 did not change. Again, the way I like to think of it, if you have trouble telling if something is the negative of the original, take the original and put a negative 1 outside it. And then if you distribute or multiply that original by negative 1, in this case, you would get negative 9x cubed minus 3. That's not what I have there. I have plus 3. So that's not going to be odd. That means this guy is neither. Third one. Of negative x. Negative of negative x cubed. And each time, notice when I'm substituting that negative x in, I'm using parentheses around it so I'll make less mistakes with my signs that way. So see, in the numerator, negative x cubed is a negative. And times that negative 1 on the outside, that's just going to be a positive x cubed then. And in the denominator, negative x squared is positive, so it's going to be 2x squared plus 6. Now I go through my investigation. Is it the original? No, it's not. This one had a negative in that numerator. It's not the original, so it's not even. Is it odd? Is it the negative of the original? Yes, this one is the negative of the original. This that I ended up with is -1 times the original function. Sometimes, again, odds are tough to tell, especially when we have a fraction. Sometimes just take a moment to go back to your original and just say, what would this be if I multiplied it by a -1? And if I multiply this by a -1, it would change that numerator to a positive. The -1 would not go to both numerator and denominator. It would go to the numerator or denominator. And we would end up with that x cubed over 2x squared plus 6. So we definitely have an odd one here. Polynomial graphs. The reason I wrote the problem this way, just sketch the polynomial. Sometimes we'll see this problem where we're asked for all the specifics. In other words, find a power function in behavior, the zeros, touch and cross, y-intercept, sketch the graph. It's kind of leading us into what we need to do. This one doesn't lead us in. It doesn't say find all these pieces, then graph. It just says, hey, sketch that graph. Okay. So one of the reasons I wrote it like this is because, all right, now we need to remember, make some extra notes on my paper there. I need all of those pieces to know exactly where the graph is sketched. So the power function would be the highest power if it were multiplied out, and that would be x cubed. And it is most definitely a cubic. However, the other piece I put in this problem, it would be negative x cubed. There's a negative in front of this x. So I hit a negative in here. Didn't really hide it. I mean, it's sitting there, but it's not sitting out in front of the whole thing where we're used to seeing it. So that'll give me x squared. Here's another x for x cubed, but there's a negative there. It's that negative x cubed. The power function, just remember from the past, if you were to write x cubed, that is absolutely correct. It is a cubic function. One of the reasons we liked putting the negative there was because it would remind us that the in behavior flipped to up down instead of down up. And I know for myself, if I don't put the negative here, I tend to forget to flip the in behavior, so it kind of helps me to get that negative there. Zeros would be 2/3 and -2, real zeros. -2 from the x plus 2. This one again, you got a binomial there. Sometimes a little tougher, I think, to see the fractional ones. Another reason I put this one in here. Remember, sometimes it's nice to just go out to the side and work it out. If I set that equal to 0, you get 2/3. All right, touch and cross. This one occurred one time, so that's a cross. Occurred twice, that's a touch. Y-intercept. If I put 0 in, let's see, that would give me a 2 times a 2 squared, and that's 8. And that's what I can use to get the general sketch of my graph. I have the in behavior, I have the zeros or x-intercepts and whether or not it's touching or crossing at that x-intercept, and then I have the y-intercept. So now my graph. We got a -2, 2/3. And I'll just put an 8 right there. And we're going to go down, touch, through, cross. That will be my graph. Remember, if you're asked to graph something, you're going to be given a grid. I mean, I guess it's possible you wouldn't, but most of the time, I've rarely ever seen it when you're not given a grid. It's okay. Sometimes we end up outside the grid. So for example, when this one pulled up and it had the grid put on the paper there, it only went up to 6. Well, if that's the case, just put a dot up a little further to make it the 8. Sometimes that happens to us because they're just generic grids that go on there to kind of help for your frame of reference as far as what you're working with. And that again should be that general shape of the graph.
Can I ask a question? How do you know if it's cross or touch again?
If it's even multiplicity, it touches. So there's a power of 2. So there's 2 of them there. That's even amount. Not because the 2's even. There's an even number of them. Touch, odd number of them. Cross. There's only one of the 2/3 on there.
Thank you.
Polynomial inequality. You could go through and graph the polynomial to solve the inequality. Even said back when we were covering this, that was an option. But we actually did it using the number line, and that's what I'm going to show here. Because if you want to graph it, you can go back and do the same thing we did in this problem, graph and then look at the graph. But we'll look at the number line process we covered back in the lesson. So on this, I need to find my x-intercepts. Because if I'm saying it's less than 0, that means where it's below the x-axis. So I need the x-intercepts. X-intercepts. 3, 6. And then I draw a number line. And I want to make sure that whatever my x-intercepts are, they're listed in order. In this case, they were in numerical order, but every now and then they're not, like this one wasn't. I did the 2/3 before the -2. Make sure they're in numerical order. Okay. Then we tested a value. And we tested a value in the interval. So I'm going to test a 0, a 4, a 7, and a 20. We can select anything we want in the interval because whatever's happening to the graph, meaning is it above or below the x-axis, would be the going on in the entire interval. So I can check anything I want here below 3. I just selected 0. Same with the 4, 7, and 20. I'm just selecting a value within that interval. I need something in that interval. Oh. 0. I'm going to substitute 0 in for x, and I only care if it's positive or negative, because if it's positive, that means the graph was above the x-axis. If it's negative, that means the graph was below. I'm really not concerned about the overall value. In other words, I don't care if it's a -5 or a -28. The negative is what I care about. Same idea with the positive. So if I put a 0 in, that would be a negative. That would be a negative. That would be a negative. And sometimes it might be easier to just kind of write your signs below. Each one of those terms would be negative if I put a 0 in. So negative times a negative is a positive. Times a negative is negative. Then the 4. 4 minus 3 is positive. 4 minus 6 is negative. 4 minus 9 is negative. So let's see, positive times a negative times another negative is a positive. Now the 7. 7 minus 3 is positive. 7 minus 6 is positive. 7 minus 9 is negative. All right, positive times a positive is a positive, times a negative is a negative. And then the 20 plus, 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 all positives. Then I'm ready to answer my question. Okay? I really didn't care at the moment if this, when I started this, if this was less than, greater than, less than or equal to. Now I care because now I know what's going on in the interval. I know my graph is in the negative region, in other words, below the x-axis in the first interval, above in the second, below in the third, above in the fourth. The question is asking me where is it less than 0, where is it below the x-axis, and that would be from negative infinity to 3 in union with 6, not infinity, excuse me, 6 to 9. No brackets because I didn't have the equal to. So just remember a little bit of an aside to this particular problem. If I had seen an equal to there, it wouldn't change any of the work I did. But in my answer, I would have brackets there because it would be equal at those x-intercepts. The problem on your paper just said the strictly less than, so the parenthesis. But if I did see an equal to, it would change to those brackets. Find the zeros of the polynomial. When we're finding the zeros of the polynomial, just remember they could be real zeros, could be imaginary. In the end, if I'm asked to find the zeros, I need to figure out the possibles. P was the factors of the constant, 1 and 7. Q is the factors of the leading coefficient, 1, 2, 3, and 6. So P, factors of the constant. Q, factors of the leading coefficient. So we could have a problem that just asks us for the possibles. And so the possibles would be plus or minus P over Q. So it's each P, 1 and 7, over each one of these Q's. So that would be plus or minus 1, plus or minus 7. Then plus or minus 1/2, plus or minus 7/2, plus or minus 1/3, plus or minus 7/3, plus or minus 1/6, plus or minus 7/6. So a lot of possibilities here. When I've seen questions show up on the final that just ask to list the possibles, in other words, not solve, just list out what these possibilities are going to be. A lot of times there's been kind of a healthy list just to kind of make sure you get them all. In other words, there's more values, a lot of fractions. Okay? Typically, when I see a question that says find all the zeros, there's not this many to choose from. And that's because they don't want you spending 30 minutes trying to find a synthetic division that works to give a zero remainder. So I kind of mixed some things in here. I wanted to get some fractions. I wanted to show a lot of possibles and stuff. So we ended up with a lot of them and then how to use them. But just kind of rest assured, if you're asked to solve, you're not going to have, or typically not have, this big a list with all these fractions. If you're asked to just list the zeros, which I've also seen, then yeah, you might have a pretty healthy list, but then that would be where you'd stop. It was just asking you to list the zeros. So once I have my possibles, this is where I have to go through, start my synthetic division, and then see if I can get one that ends up being a zero remainder. So my synthetic division, set it up, 6, 25, 12, -7. Now in the process, this is where you are selecting one of these possibles. You want a zero remainder. If you select one and you don't get a zero remainder, you go back, pick another one. All right, you got to keep going till you get one. And now I'm going to cheat here because I know -1 works. Okay, but let's face it, I'll tell you right now, I probably would have tried 1 first anyway, and then -1, because I'm probably not going to try a fraction first, even though they might work or are going to work here. But I'm typically going to go smaller numbers. They're quicker. I think you would do the same too. Okay. So 6, -6, 19. Let's see, -19, -7, +7, 0. There's one of the zeros, x minus 1, or excuse me, yeah, negative x equals -1. Now this was my depressed equation. That depressed equation, I'm going to look to factor it. If I can't factor it, then I've got quadratic formula that I can use or what have you. So factoring this, let's see, and I'm going to 3x, 2x, 7, 1. And that will be a plus and a minus to give me a 21 minus 2. All right, that's 19. So this is going to give me the other two zeros, 1/3, -7/2. Sometimes, again, the fractions are kind of a pain. If you go out and just set 3x minus 1 equal to 0 and solve for x, you'll get the 1/3. 2x plus 7 equals 0. Solve for x, you'll get the -7/2. So there's my three zeros. What that also tells me is in the synthetic division, the 1/3 and the -7/2 that would have worked in there. Okay. Now, as far as solutions, right, these are my three solutions. The problem asked you to find all the zeros. Hey, I found all three zeros. I knew there was going to be 3, power 3. My zeros are -1, 1/3, -7/2. You can circle them like that. You can go write x equals -1, x equals 1/3, x equals -7/2. Any of those methods would be fine, but I need those zeros. Now, if you have a question that says, write solution in factored form. Every now and then we see this. It's most of the time we're just asked for the zeros, but I think on a couple of the other reviews you might see a question that says, hey, write the solution in factored form. Don't change anything you're doing. We have our three zeros, -1, 1/3, -7/2. Factored form would be -1 came from x plus 1. 1/3 came from 3x minus 1. And -7/2 came from 2x plus 7. That would be the factored form. If you write both, that's fine. Typically, again, we're asked for the zeros. But I just wanted to add that in there on this problem in case you see one that says, hey, write in factored form. Well, how come they did this and didn't just have the three numbers? Because it's set in this factored form. Getting that look there. The next problem is an exercise in dealing with that factored form. So let's see here. Make sure I got that right. 8. We've got zeros of -3 and 3 minus 2i. That's the two zeros that I'm given. There has to be 3 zeros to this. So what we need to remember is the imaginaries, complex numbers at 3 minus 2i, must exist in a conjugate pair. So I know that there's also a 3 plus 2i. Those would be my 3 zeros. Now it's asking me for the polynomial. I've got to make sure I get the setup right. -3 comes from or came from x plus 3. 3 minus 2i came from x minus 3 plus 2i. And 3 plus 2i comes from x minus 3 minus 2i. We've got to make sure we get that set up right. Okay? All the multiplying, I'm not going to say it's easy. It is definitely very tedious, but multiplying is something you've done many times. If we don't have the setup right, it doesn't matter how good we are at multiplying. we're not going to end up with the right answer. So I've got to make sure I get the setup right. Just as a reminder, this is where that's coming from. If we're saying x equals -3, that means x plus 3 is 0. There's where I got that x plus 3. If I'm saying x equals, what's the other one? 3 minus 2i, bring both those over to the left side, I'd have x plus 3, excuse me, x minus 3 plus 2i equals 0. Both those signs will change. That's where I got this one. And then for the other one, x equals 3 plus 2i. They both go over to the left. X minus 3 minus 2i is 0. There's where I got those setups. Sometimes we get ones that we see something like a -3, and we might be pretty quick. Hey, x plus 3. And then we get sometimes a binomial where we struggle a little bit. Hey, take the time to write it out. Bring them back to that left side. All right, now the work comes in. I've got to get this multiplied out. You can multiply any ones together first that you want. My suggestion would always be multiply the complex ones first. Only because polynomials do not have an I in them. So when I multiply those two out, there shouldn't be any i's left over. That's kind of one checkpoint, something canceled out. If I'm left with some i's in there, I made a careless mistake or did something wrong. I did something wrong carelessly, or maybe my setup was wrong, but something's wrong. So I'm going to distribute then my x through each one. So that would be x squared minus 3x minus 2ix. Come back, distribute my -3. -3x plus 9 plus 6i. Back, distribute my 2i plus 2ix minus 6i. And in the last term, minus 4i squared. And again, this would be my checkpoint. If all of those i's don't cancel, okay, and I've multiplied these things out many times before, and I tell you, still every now and then, man, I got a sign wrong because it didn't cancel. Right? Doesn't matter how many times you do it, we all make careless mistakes. Make sure those i's are canceling. They're subtracting out. If they're not, we got a mistake somewhere. So let's see, -2ix and 2ix, those go. Positive 6i and -6i, those go. And then that I squared. We need to remember that I squared is -1. So that's really -4 times -1, which is +4. I squared is that -1. So that's going to give me a +4 on the back end. So now here comes my x plus 3. And let's get our terms together. We got x squared. Let's see, -3x and -3x is -6x. 9 plus 4, 13. And again, you get problems like this, and we've seen a few others here where you've got several steps on a test. Write out your work. Okay? Show your work. Because sometimes it's a careless mistake, and we still give some partial credit there if we can see where that mistake was. All right, now I'm going to distribute my x. So x cubed minus -6x squared plus 13x. Distribute my 3 plus 3x squared minus 18x plus 39. And let's see here, that would be x cubed minus 3x squared minus 5x plus 39. over 9. That's the rough sketch of the graph you have on the paper. Again, some of these graphs, I'm just getting a rough sketch up here. Probably better to look at them on your paper there, so you see the values a little bit easier. So we did graph rational functions, but sometimes we get asked something to evaluate in reverse. In other words, hey, here's the graph. What equation could this have come from? Now that's a little bit different than what we were asked in the past, and why I put this on here. I wanted to make sure we get one in here working in reverse. Okay. This has been seen recently, right, as far as creating the equation. And so I provided a couple hints there. I said, first, think about the asymptotes. And second, think about the x and y intercepts. Okay. So if you list those out, they'll help you create the equation. So the vertical asymptotes would be, I don't have any numbers on my board here. Let's see. Would be at x equals -2 and x equals 3. I can see on my graph again, you've got numbers on your picture there. The horizontal asymptote is at y equals 0. That's referring to that end behavior. The x-intercept is at 2, 0. And the y-intercept, 0, 1/3. Now, a lot of times when we're looking at intercepts, we'll see it go right through an easily defined point. Okay. This particular one I had come up, ended up going through about 1/3. If it ends up being a fraction, like it is here, somewhere between 0 and 1 on the y-intercept, don't panic. Feel free to just estimate what that value is going to be. There wouldn't technically be a wrong answer in that case if you said it's like a half or something like that. It looked a little bit lower than a half, so that's why I said 1/3. Okay, but if you're close on the estimate, you're fine. Now, those are the pieces that are going to help me create the equation. So, f of x. Vertical asymptotes are the domain restrictions, so they were on the denominator. So if I have a vertical asymptote at -2, then there must have been an x plus 2 down there. If I had a vertical asymptote at 3, then there must have been an x minus 3 down there. Horizontal asymptotes. If the horizontal asymptote's at 0, that meant the power of the numerator was less than the denominator. If it's a value like a 2, that means the powers were the same. Leading coefficients gave the horizontal asymptote. And if there is no horizontal, that meant the power of the numerator was greater. This one has a horizontal asymptote of 0. That means that numerator power must be less than the denominator power. So in this particular case, that denominator power is x squared. I know I have x plus 2 and x minus 3, but if those were multiplied out, it would be an x squared. So that means this must be a power of 1 sitting up in the numerator. Now, at the moment, I don't know anything else other than there's a power of 1. I don't know if it's x plus 7, x minus 5, anything like that. I'm just working with those asymptotes. Now come the intercepts. If the x-intercept's at 2, 0, that meant the numerator had to be x minus 2. The x-intercept came from the numerator. So x minus 2 would produce an x-intercept of 2. Y-intercept. I said 1/3. Again, I had to estimate that. Right? The graphs that we typically see on the test, it's going to be a lot more obvious what the value is versus a 1/3. Alright. So let's see what happens if I put 0 in for x though. I would have -2 up top in the numerator. I would have 2 times -3 is -6. Hey, -2 over -6 is 1/3. There is an equation of that graph, a rational equation of that particular sketch. Hint. Find the inverse of this exponential function. Now, typically, you get a final exam and it combines, just trying to combine all the stuff that you did. And granted, there's always a couple things that get left out. You can't really do everything. But sometimes you can get a question where it's combining more than one thing, right? And this is an example of that, where it's combining more than one thing. Okay? It's finding the idea of an inverse. An inverse was switch x and y, solve for y. So to find an inverse, we switch x and y, solve for y. Inverses were typically done with just regular, I say regular, just generic functions, not e's or logs. So sometimes we'd have one like this, and we switch x and y and solve. Okay? This is bringing in the idea of the exponentials with this piece. Okay? Looks a little worse, but the idea of finding an inverse of an exponential tells me it's going to be a logarithm. Those were the inverses. Exponentials were inverses of logs. Logs were inverses of exponentials. It's not changing how I do this. To find an inverse, I switch x and y. So x equals e to the 2y plus 1 plus 3. X and y are switched. And then I solve for y. So the quick, easy part, switch x and y. The work, solving for y. So we got to work to get y alone here. Subtract my 3 over. X minus 3 is e to the 2y plus 1. Now I need to solve for y, so I'm going to have to get that exponent, that 2y plus 1, out of that power so I can work with it. Because I'm somehow, sooner or later, going to have to subtract the 1 and divide by 2, but I can't do it when it's up in that exponent. So this is where we use the logarithm. ln of x minus 3 is ln of e to the 2y plus 1. The purpose of the logarithm, using that property, was so that the power will move into the front. So now I have ln x minus 3 equals 2y plus 1 ln e. Ln e is 1. So now I have ln x minus 3 is 2y plus 1. Now, at this point, I had quite a bit of work there, but at this point, it's not too bad to get y alone. We're going to subtract the 1 over and then turn around and divide by 2. So, ln x minus 3 minus 1 is 2y. And I'm just going to write it up here. F inverse of x would be ln x minus 3 minus 1 all over 2. Or you could even bring a half out in front. Whichever look that you like. I can't remember which look I used for the answer key. And we could do something like this. And we could even distribute that half. Any of those answers are correct, but I don't have it in front of me as far as which one I put on the key, but any of them would be fine. Using our properties. So to expand into a sum and difference using our properties, we need to remember that if I see multiplication, that would go to addition between. If I see division, that would go to a minus. And that being said, this would be log of 2 base 5 plus, because that was 2 times 1/2 log of x base 5 minus, since it's on the bottom, log of y base 5. A lot of times we'll see radicals show up like that square root there. We want to remember that. That means it was a half exponent. The square root of x was x to the 1/2. Had a cube root, x to the 1/3. Right? Sometimes we'll end up with the numerical part. And a lot of times you get asked, hey, you know what? I see that log of 2 base 5. Do I need to simplify that out anymore? If it comes out to a nice integer, yes. In this case, it does not. Okay. If I use my calculator, my change base formula, and did log 2 divided by log 5, I'm going to get this long decimal. That would be that simplified form. Now, just to kind of make a little change here to kind of show you the difference. If this had been a 25, then I'd have a 25 here. That would simplify to 2 plus 1/2. So I would want to simplify that piece. If I had a 25, do I expect you necessarily to know immediately right off the top of your head? Log of 25 with the base of 5 is 2. No, but you can figure that out in the calculator if it comes out to a nice integer. So I would want to simplify that one to 2. But in the case that we had in the original problem there that you had was just a 2, not a 25. And that's going to come up to a long decimal. Again, if you don't realize that, once you put it in the calculator, you'll see a long decimal. And the simplified form was a log 2 with a base 5. Right? I'm going to look at a couple more here. 12. Just to kind of, and mainly just to kind of finish up this unit. Okay. So these e's, e to the 2x minus e to the x minus 12. This factors. This first one is the square of the second one. So I can factor this. Let's see, that would be a 3 and a 4. So I'd have a minus 4 and a plus 3. That would give me a negative 1 in the middle. So now if I set each part equal to 0, because I've got to finish solving for x here, minus 4 is 0. All right, this would be e to the x equals negative 3. And this one would be e to the x is 4. So now I'm looking at this, go, wait, e to the x would never be negative 3. This has a no solution. I can't solve that. If I don't recognize that right away, there's no panic there. I can take the log of both sides. I can bring that x down. X ln e, well, that's 1. Is ln negative 3. And if I go put ln negative 3 in my calculator, it's going to give me an error message or something like that. So that's why I know that one's a no solution. The second one, let's see. ln e to the x is ln 4. So x ln e is ln 4. The ln e is 1, so that would be x equals ln 4. Or an ln 4 is fine, whatever decimal that is. I don't have my calculator right with me at the moment, so whatever decimal that is. But we would have that ln 4. $13. This will be the last one we'll look at here today, because this will be the last one from that exponential unit. Okay. All right, how long will it take the population to reach 1 million? Unfortunately, the part that I don't have here is K. I need to know what the constant is. So in this case, I've got to find out what the rate is. Need K. We have seen where we're asked to find K and we're given, say, a half-life on a problem, something like that. This one didn't give me a half-life, but it did tell me 140,000 bacteria grow to 609,000 after 6 hours. So I do have a relationship that's going to give me that K value. Okay. So my setup would be 609,000 equals 140,000 e to the 6K. It happened in 6 hours. I'm going to solve that for K. That's going to give me my rate. So 609,000 over 140,000 equals e to the 6K. Up to you. If I know I'm going to be using my calculator, so if I have a fraction I can simplify, I will. If I want to go to a decimal, I can. In this case, since I don't have my calculator, I'm just going to write it 609 over 140 equals e to the 6K. And that would mean that K, after I do my logs, would be ln 609 over 140 all over 6. There's that K value. Right? Now, remember, once you find the K value, it doesn't matter if you use it in this format or if you go get a decimal. And I tell you, sometimes when you got an ugly looking format like this, a lot of times it's easier for us to go to decimals. The only thing I will state is just don't round off early. Get it out there to say 5 decimal places or whatever. Make sure you're carrying that out some so it holds that final answer to be a little bit more accurate. Now let's go deal with what we're asked for. We're asked how long will it take for there to be a million? So 1 million equals 140,000 e to the K. So this is my K value. ln, be kind of small here, but ln 609 over 140 all over 6 times t. So that's all up in that power there. And again, using a decimal in that situation is fine. Okay. So I got to work to solve for t. First thing I'm going to do is divide over the 140,000. So 1 million over 140,000 equals e, that K value up there. Let's see, I'd probably take out the 4 zeros. So, like I said, you can go to a smaller fraction, leave it the large fraction, go to a decimal. That's not going to matter. Okay. So 100 over 14 e to all of this. Then we'll use our logs, bring down, divide. So we would have ln of 100 over 14 all divided by ln 609 over 140 over 6 equals t. So ln of this divided by that whole k value is going to equal t. And as far as all the little specifics, I didn't have my calculator in front of me, but I do remember from the answer key, it was like 8.02 hours. That's what I had down there for that piece. All right, that's going through all the steps of the first 13 problems. Okay. Hopefully, as you were looking at that before coming into this, that maybe gave you some clarity on some where you were having trouble, or even verified where you were doing great and ended up getting those answers as you were looking at those problems prior to seeing this. As far as going through those. All right. Next time we'll just pick up at 14 and we'll go through those others. So suggestions would be these 13. Okay. You can go back, review this video, what have you. And then you can at least pause and do some things like that, take it a little slower in some areas. Okay. Make sure you have these types of problems down. Go to some of those others that I reviews or other example things that were sent out. Look for these type as far as trying some in this nature that will help you out there. If you need some extra practice on a certain type, like maybe this one or this one, whatever the case is. Okay. But your focus right now would be on those problems. Okay? Once those are down, then the focus would be on the next part of this review piece that we're looking at, which would be 14 through, or the final was 14 through 22, looking at those.